Hello. So, welcome. This video is going to discuss numerical differentiation. So, how do you get the computer to do calculus? Before we get into this too much, I want to first just kind of remind you guys what happens when we take derivatives. So, we're going to go over here to, to the whiteboard space here. And as I see, there it is. Okay, good. I lost it for a second. So in the whiteboard space, I'll be able to kind of show you. So just to remind you guys, the idea of a derivative is as follows. If we have a function, sorry, having a little computer difficulty here, so I'll try it again. Whiteboard share. Okay, I think we're working now. Okay, so if we have a function, so let's just draw some axes here. So let's imagine I have a function. Maybe we change some colors. Okay, so I have a function here. Like that. And let's imagine that I mark out a couple points here. So the first point is going to be in black, and that's going to represent the point that we actually care about. And I want to mark out a couple other points. Well, let's choose blue here. We don't use blue very much. So I've got a point up here, and roughly speaking, I'll have another point down here. Okay, and sure, hope no one's colorblind. So labeling points here, I have point X here, and this point here is going to be, it's a little bit farther along, so I'm going to call it X plus delta X. So delta X is this distance. And similarly, I can do the same thing here. And I want these to be symmetric, so this would be also of width delta X. So this would be X minus delta X. Okay, so I've got 3 points. I'm going to use them to describe derivatives. So the first off, the real definition of a derivative is, well, remember, the derivative. So if I call my function f of x, then I would say that the derivative f prime of x equals, and I would say it's equal to f of x plus delta x minus f of x divided by delta x. But I forgot. I'm doing calculus, so really this is the limit as delta x goes to 0. Now, so that's the definition for the derivative. There's another way you can define it, which is completely equivalent in the limit. So as long as you have that limit there, it kind of covers up all sins. I could also say it's equal to f of x minus f of x minus delta x over delta x. So look at that. Here I have x plus a little bit minus the original function value. In the other definition, I take the original function value minus f of x a little bit farther back behind. But when you take the limit as delta x goes to 0, it doesn't matter because both of them are computing the slope of the secant line, or of the tangent line, sorry. So they're all estimating, or well, it becomes exact in the limit, but they're all calculating the slope at the point in the middle, which we're calling x. All right, well, our numerical methods are going to be, so a computer can't do calculus. It can't handle this continuous bits of information or pieces of information because it has to be broken down into discrete binary bits, ones and zeros. So you can never really take a limit. So we're going to have to make approximations so that a derivative won't be exact, but you know what? If you make delta x really small, if you kind of slide this blue dot closer and closer and closer to the black dot, then the errors are going to get smaller and smaller and smaller. So what we're going to do is define two kinds of derivatives. We're going to define the forward derivative with a plus on the function, and that's simply going to be f of x plus, I emphasize, delta x minus f of x divided by delta x. That's the forward derivative. And then we have a backward derivative. And we'll call that nabla, or whatever. Nabla is what the symbol is. Minus f equals, and that's going to be f of x minus f of x minus delta x, all divided by delta x. Now, these two formulas look very similar to these formulas, but they don't have a limit. So it's the calculus without the calculus. There's no limit involved. And so these are not going to be exactly the derivative. But the idea is that if the function is smooth enough, and if you make delta x small enough, this gives you a good enough approximation. So the forward derivative, change colors here, we'll do the forward derivative, we'll do this one in blue, I guess. So this one will be in blue. It actually computes the slope of the line right there between the black and blue dots. Whereas the backwards derivative, we'll do that one in brown, that computes the slope of this secant line. Oh, I apologize. And if you make delta x go to 0 fast enough, then the slope of the blue line and the slope of the brown line all converge to the slope of the tangent line, and you get the same answer. Okay, so these are going to give us, these two formulas give us our basic building blocks for doing calculus with a computer, and we're just going to write little functions to encapsulate these formula ideas. So hopefully these are pretty intuitive, even if they're not familiar to you. Okay, so let's go back over to the Mathematica program. Okay, so here we are back, and I just, at the top of the file here, I kind of remind you guys the definition, both definitions of a derivative, and how they agree in the limit. And now, Mathematica, and there's a similar kind of program called Maple, and there's also MATLAB, and then there are some other free ones. But these, they can all handle symbolic calculations. So they are able to do some symbolic calculus, but most programming languages cannot do that. So instead, you have to use these approximate formulas. And we've done it. We've used the the derivative function a little bit in Mathematica. You know how that works. This is how you would work in most other cases in C, Fortran, Python, any of those languages. Okay, so what I'm trying to do, here's my forward derivative, sorry, I shouldn't say forward derivative, forward difference derivative. And so f plus of f, and what it should do is evaluate f of x plus a little bit minus f of x divided by the little bit. So I've written a little function here called f deriv for forward derivative. And the arguments are the name of the function, the point that you're interested in, and your delta x value. Remember, we're going to choose delta x to be something small, 0.01, 0.001, 0.0001. Make it as small as you can, but it won't ever quite go to 0. Okay. And here I've got a little example. So we're going to apply this forward derivative function on sine of x. Now, so that's easy enough to do. Here we can just check that. So let's just move this over for a second here. We'll put that up here. So define sine of x, and then we could just say, how's that going to work? We'd say, well, f deriv of f, comma. Let's say we want the derivative at x equals 1. I don't know. And let's say that our delta x is 0.0001. Oh, wrong button. 0001. Okay? And then let's see what it tells us. Well, let's see if I not do something right. There we go. That's what it says. Let's see if compare that to the exact value. D on f of x evaluated at x with respect to x. Sorry. So we're going to take the derivative of the function at x and then replace x with 1 after the fact. Let's see what we get numerically. Oh, keep forgetting that. Okay. Oh, do you see my problem? I forgot a decimal point. Now we're cooking. Let's try that again. Sorry about that. I forgot my decimal point on my delta x. So delta x wasn't getting small. It was really large. So let's try that one more time. My numerical discrete or forward difference derivative. There we go. Much better. It evaluates to 0.540298. Good. Whereas using Mathematica's built-in calculus tools, the exact answer, well, to this many digits anyway, is very close. And if I made my delta x even smaller, I bet I get even closer. Oh, now I'm really good. And whatever, you can get more and more accurate if you wanted. Yeah. So it's within the, so unless we set it to give us more precise answers, that's what we get. Okay. Now, talking about errors, it turns out that this forward difference derivative, it has an error, and it turns out the error is proportional to delta x. So to the first power. The first power, that's important. So, because in a minute I'm going to introduce a different type of derivative, which is has an error that goes proportional to delta x squared. And if delta x is small, that's an even more accurate approximation. Okay. So, oh dear, I fouled that up. There you go. So what I've done here is written a little loop to kind of explore the effect of having different sized delta x's. So I made an array called errors, and then we're going to go through a loop, and in each iteration of the loop, we're going to make delta x smaller and smaller and smaller. It's going to start out as like, I don't know, 0.001, no, 0.01, then 0.02, or sorry, 0.001, then 0.0001, then 0.000, whatever, you get the idea. So you can make delta x get smaller and smaller and smaller, and we're going to evaluate the forward difference derivative on the function and compare that to the exact derivative of them, okay, using Mathematica's tools. And then what I'm actually going to do is compute the percent error or percent difference by subtracting the exact value minus the approximate value divided by the exact value times 100. And we're going to plot that for different delta x's. Now, as we go through these sequence of points, delta x is getting smaller and smaller and smaller. Just remember that. Okay, so then I make a graph. And so at the beginning, delta x is 0.01, and the error is like 0.8%. And then as you, here, maybe I shouldn't have done joined. Let's make it not joined. There you go. So you can see delta x there. Then at the next power, it's 0.001, and the error is like 0.09 or something like that. And then this is, over here it would be 0.0001, and now you see the error is getting really small. And notice it's nice and linear between them. So just as I claimed, the error, the percent error, is proportional to delta x. It grows, or it shrinks linearly as you make delta x smaller and smaller and smaller. Okay, that's a forward difference derivative. Well, no surprise, all we're going to do is just change the coding a little bit, and then we'll come up with a backward difference derivative. Oh yeah, there you go. That's what I was trying to say earlier. So in the graph, you can see that the percent error versus delta x, and it scales like delta x to the first power, linear. Backwards difference derivative is really defined in an analogous way. It's f of x minus f of x minus delta x, all divided by delta x. And I just coded it in there. So I define that. And I'm going to do the same thing, and I can compute derivatives in the same way. And you see the same sort of behavior. It gets better and better and better the smaller you make delta x. You might be interested in, let's evaluate f, the forward derivative of f at 1, 0.001. And then we'll compare that to the back derivative of f at the same point, 0.001. Now, the function we're studying is sine of x. It's not a linear function. So there's no reason that these should be exactly the same, but we expect that their difference is quite small. Yeah, that's really small. The difference is very small. Remember, the exact value is d f of x at x slash dot x goes to 1 and give a numerical value. In fact, if you look at these two, you might say that the exact answer is pretty darn close to the average of the forward and backwards derivative. And that's not an accident. Okay? Both the forward and backward difference derivatives have linear scaling with delta x. So they work, but they're not super accurate. But it turns out if you take the average of them, and you just work out what that means, it actually has this formula. If you take the average of the forward and the backward difference derivatives, the errors cancel out, at least at linear order, and the error bars, or sorry, the error scales like delta x squared, so it's quadratic in the delta x step size. So I just did that. So you could just code it in there. It turns out when you take the average of them, the middle term cancels and you get f at x plus a bit delta x minus f of x minus delta x, all divided by 2 delta x, and it'll be even more accurate. Or since I had already defined these functions, I went ahead and just took the average. It works out the same. So if I go through, I can do the same thing and evaluate the same derivatives. And let me get rid of this joined because it kind of maybe obscures things a little bit. I don't know. And you'll notice, look what happens. The function's here, it's coming in. You might have said it was linear, but actually it curves here. And when you get to small delta x's, when you make delta x really small, it actually is quadratic in the way that it behaves. Yeah, so the percent error gets this, goes to 0 very fast. That's really nice. So that's a nice thing to know. It's called the central difference formula or central difference derivative. And depending upon the applications, you might want to use that one. As far as second derivatives, well, second derivatives are just derivatives of derivatives. Same thing is going to be true with forward and backward difference derivatives. It turns out, and there are a couple ways you can do this. This is not the only way. And again, I'm really just trying to give you guys an introduction to a whole bunch of concepts here. The central formula, central valued formula for the, symmetric formula for the second derivative is what you get when you apply the forward derivative on the backward derivative, or you can go the other way around. You get the same answer. And it ends up being f of x plus delta x minus f2 f of x plus f of x minus delta x, all divided by delta x squared. Okay. So, so I have that f dBd, forward derivative, backward derivative, and basically what it does, and I'm just using the derivatives I've already defined. So I start with a function f, I evaluated the backward derivative on it, put that into something called temp, and then I evaluate the forward derivative on temp. It's not the only way to do it. It's kind of crude, but it gets the job done. And it gives exactly the right formula. This formula matches what it's supposed to. Or I could have just typed in this formula directly. I guess I just wanted to show that what I claimed was true is actually true. Okay, so that's going to be my second derivative. FdBd is my second derivative. And because it's, again, I can compare how it does to the exact derivative using the D command. And I see that the central or symmetric second derivative has an error that scales like delta x squared. So it's a pretty accurate formula. There are other formulas for the second derivative. There are higher and higher formulas for the second derivative. And they have different applications. If you do more and more complicated simulations, you might have a need for those, but for our class, this is what you would need. Okay. All right, and we come to your homework for this activity. In this, there are two problems. In the first problem, you will use the derivatives defined in the notebook, so they're already handed to you, and apply them to a really gross function. So sine of cosine of arctan of sine of cosine of arctan. Make a plot of this function, and on the same graph, plot a line which is tangent to the curve at x equals 1. And to estimate that curve, use any of the derivatives you want. You can use the forward derivative, the backward derivative, or the central, or the symmetric one. What do we call it? The central difference derivative. But don't use Mathematica's D command. Use the difference derivatives to plot a point which is tangent to that curve. And then I want you to go through and add comments to explain to a future user how the first and second derivatives work. You should comment on the conceptual origin of each, as well as how they're encoded in the notebook. And when I say conceptual origin, I just mean going back to what I described in this video with calculus, but then don't actually take the limit. So go through and really just kind of understand where these formulas come from. So take these difference derivatives, apply them, and show that this formula is correct, things like that. Okay, so that's all for this one. Shouldn't take too long. Hopefully this stuff makes pretty good intuitive sense to you.